All right, so I am gonna start here, and then if you have questions, but hopefully I'm gonna go through some of this stuff. So reference table, so you should know what to use each reference table for, right? So table A is basically standard temperature and pressure, right? So you should know how to convert between atmospheres and kilopascals using that. Remember when I went over that before? I don't know if you remember it or not, but you should know how to use table A to do that. Table B, if you're asked to do a heat calculation, okay? So you absolutely should know how to do a heat calculation using that. Let me see, let me change this. Okay, so for table B, there we go. No, I get there eventually. Okay, so for table B, you need these for those heat calculations, right? So, and I think you did that relatively recently in lab, yes? Right? Where you use these formulas, Q equals, right? Yeah. So this is where you need the stuff for water, okay? If it's not on here, like if you were asked about a different substance, they would have to tell you what the heat of vaporization was, or you would be finding it, okay? So know that these are here. Table C, you barely have to use, but you could have to use kilo or milli for conversions, okay? So do you remember how many milligrams are in 1 gram? Right, so if you remember 1,000, anything that's milli, right? In 1, whatever it's gram, liter, right? And then how many like grams are in 1 kilogram? Also 1,000, right? So really the only two that you have to know would be, so there's 1,000 like base units in 1 kilo. So if this is like kilograms, 1,000 grams in 1 kilogram, right? These two, if you remember these, so this could be grams, it could be liters, whatever, meters, right? Those units. If you remember those two, you can pretty much do any conversion they're going to ask you to do. All right, so knowing those is helpful because sometimes it's hard to interpret this table. And I don't really see them using other ones, at least for conversions, okay? Then when we get to table D, basically if the question says, what is the unit for, and you didn't turn to this table, then you weren't doing yourself a favor, right? With remembering this, millimeters of mercury is pressure, okay? The rest that you're asked pretty much are on here, okay? I mean, degrees Celsius is not on here, but most of the time people realize that's temperature also, okay? But if that's for a unit, you should be looking here. Table E, so all these are polyatomic ions. Here's what's important to remember. They are covalently bonded to each other. So if we look at a simple one, right? So if we look at, we have carbon, it's going to be bonded to nitrogen. Overall, the whole thing has a negative charge, right? The bond between them is covalent. But if we have this, like sodium cyanide, right? Inside the CN, it's covalent bonds, right? But the attraction between this positive and negative is ionic. So sodium cyanide has both ionic and covalent bonds. Okay, so anything that is on table E is going to have both ionic and covalent bonds when it's in a compound. So it could be potassium nitrate. Nitrate's on table E, so in a compound, potassium nitrate has ionic and covalent bonds. Okay, if they ask you just about the polyatomic ion, it's covalent bonds. So in nitrite, it's covalent bonds. In phosphate, it's covalent bonds. Okay. But when it's bonded to something else, now we have both, okay? that's something that is like a pretty frequent question. We did solubility with this table. Look familiar? Yes. Okay, so remember the rules. If it's in this side, the rule is that it's soluble. The easiest thing to look for is anything that is right here because they have zero acceptance. Okay, so if I have Na3 PO4, well, Na is here and PO4 is here. How about if we use the Na rule because it's easier, right? So would this compound be soluble or insoluble? Soluble, right? If I have, let's see, that's ammonium sulfide. Which ones are on the table? Well, both ammonium and sulfide, right? But ammonium has no exceptions, so use that one. It's soluble. I mean, it works for this one, but you have to think about the rule. So sulfide's rule is that it's insoluble, but ammonium is an exception. So it breaks that rule, right? And it becomes not insoluble, but soluble. But you could have just done it by looking at this. So what would, let's see. What would this one be? Well, do we have magnesium anywhere on the table? No. Is magnesium in group 1? Because remember, they don't list all of group 1 here, but is magnesium in group 1? No. So that means I have to go by carbonate's rule, right? So you see carbonate on the table? Yeah. Its rule is that it is insoluble, but it has exceptions, so I have to check. So what is it combined with? It's combined with this, right? Is magnesium in group 1? No. Is magnesium ammonium? Like, is this the same as that? No. So that means it can't break the rule, it keeps the rule. So this one will be insoluble. Insoluble. Okay. All right, that's basically how to use that table. Then we go to table G, which is solubility. One thing I said here, pay attention to this because on the table it says it's 100 grams of water. So if you have less than 100 grams of water, then it's going to be less. That can dissolve more than 100. So let's say we have this much ammonium chloride right here. So at 80 degrees Celsius, we've added like 67 grams. Will this solution be saturated, unsaturated, or supersaturated? If this point is like exactly where it is. So it's at 80 degrees Celsius and it contains like 67 grams. So just saturated because the point falls literally on the line, right? So if it was 67 grams, right? But what if I only had 50 grams of water? Well, I need 67 grams if I have 100 grams of water, because that's what this graph tells me. So what would I do to 67 if I only had 50 grams of water? Divided by 2, right? If it was 200 grams of water, you multiply by 2, right? What if the point is anywhere above the line? What do we call it? Supersaturated. What if it's anywhere under the line? Unsaturated. So unsaturated means more will dissolve if I just add it, okay? How do you make supersaturated? Like you heat it up, like too hot, dissolve extra, then cool it down slowly, okay? Also, you should know that most of them that go down like this are gases. So as the temperature of a solution increases, the solubility of a gas decreases, okay? The solubility for solids will increase, all right? The other way that they could ask it is like, which salt has the lowest solubility? So you have to know that salt means ionic, okay? So when I start looking for, say, at 80 degrees Celsius for the salt that has the lowest solubility, the first thing I hit is SO2. Well, SO2 is a bunch of nonmetals. That's not ionic. I go to the next one. That's NH3, also a bunch of nonmetals, not ionic. Finally, I get to NaCl. Okay, that one is ionic, metal and nonmetal. Okay, so just be aware that a salt means it has to have ionic bonds, which usually means metal and nonmetal. Or alternately, a polyatomic ion. So it could have a polyatomic ion in there. But in general, it's going to be a metal and a nonmetal. Okay. Table H, I call it, this is like the forgotten table. A lot of people like legit forget about this table on the exam. If a question is asking you anything about vapor pressure, please turn to this table. The answer is literally probably here, straight on the table. You should know that this dotted line represents standard pressure. So anywhere that these substances cross that dotted line, that is their normal boiling point, because normal boiling point is at standard pressure. Okay, so the normal boiling point for ethanoic acid is right there. For water, it is right here, which is 100, which you should know that, right? The normal boiling point of water. The other thing which you kind of should know about this table is that if there are more intermolecular forces, the boiling point will be higher. And they like to ask this question in a number of ways on the exam. So like at 75 degrees, which one has the highest intermolecular forces? Well, you look for the one that has, well, at say 150 kilopascals, which one has the highest intermolecular forces? It's going to be the one with the highest boiling point. Or here, this one right here has the highest intermolecular forces. Okay, so this one here, highest intermolecular forces, because it has the highest normal boiling point. Okay, so which one of these would have the lowest intermolecular forces? Oops. One at the other end, right? So always this one and this one, right? So lowest intermolecular forces, highest, okay? Table I, remember, we looked at this several times. It says a minus sign indicates exothermic reaction. So literally it tells you if the reaction is exothermic or endothermic. If they ask you randomly on the exam, is this reaction exothermic or endothermic? I promise you, you didn't have to memorize it. It's on table I. Okay, so you just have to look it up. And if it takes, like, I'll just use this one as an example. If it takes 182.6, this is in kilojoules, to make 2 moles of NO, how many joules does it take to make 1 mole? What would I do? Divided by 2. That question they ask a lot, okay? If they ask me how much to make 4 moles, well, then I multiply it by 2, right? So you should definitely know how to use that. You should also be able to sketch a potential energy diagram. So if they said sketch a potential energy diagram for this one, which I know it's this, well, a potential energy diagram has reactants, right? And then they all have like a part that goes up. This is the activated complex, right, at the top. If it is endothermic with a positive, that means the products have more energy than the reactant, so it's going to be like this, okay? If it had numbers on the graph, this is 182.6. Like that's where that number is. That's the difference between products and reactants, okay? Does that kind of make sense for that table? It has like a lot of side uses for that table. For table J, we just did this relatively recently. Things to remember, the higher metal is always negative, always, 100% of the time. If it's voltaic, the higher one is the anode. If it's electrolytic, the higher one is the cathode. But regardless, it's negative, okay? And then you just look for which one is higher, which one is more active. I think this table is relatively straightforward. Do you know how to apply it to like electrochemical cells? Yes, no, yeah. Like if you have like copper and magnesium, right? Which one will have the negative charge? Magnesium, because it's higher, right? If it is then a voltaic cell, this one is the anode, right? If it's the anode, what occurs there? Oxidation or reduction?
Oxidation.
Right, because that's an ox, right? So this is oxidation, which means this is the cathode. So electrons will flow from which piece of metal to which piece of metal? From copper to magnesium or from magnesium to copper?
Copper to magnesium.
Always anode to cathode, right? And then what happens to the size of the cathode? Good, it increases. Remember fat cat, right? So the size is going to get bigger, which means this size has to get smaller, right? And the electrons always go through the wire, right? What travels through the salt bridge? Not electrons. Oh, yes, the electrolytes, the ions, yep. So they're going to go through the salt bridge, yep. Okay. Acids on table K, this is relatively straightforward. Funky one right here and right here, just recognizing that they don't all have to start with H as they're written, right? So just remembering those two is key. You should know the difference between an areneous acid and well, they won't say the name Bronsted-Lowry. They will say another theory or acid-base theory. If they name it, they mean areneous, okay? Areneous acids they have H plus ions, yes, as the only positive ion. Bronsted-Lowry acids are H plus donors. That literally means the same thing, right? So areneous acids have H plus as the only positive ion, and Bronsted-Lowry acids are H plus donors. Now, if again, for Bronsted-Lowry though, they're typically not going to say Bronsted-Lowry, it'll just say another theory, okay? Whereas when we talk about bases, right, if we're talking about areneous base, they have OH negatives as their only negative ion, but a Bronsted-Lowry base is an H plus acceptor. So the definition differs when we get to bases, okay? You don't have to, for acids, you really don't have to know other acids than what are listed, but for bases, you have to know basically that anytime you have an OH combined with a metal, it's a base, okay? Because you could have LiOH or MgOH2. So if it's a metal with OH, you have to know that it's a base, okay? Unlike for acids, they listed them all, okay? Indicators, I think you just did lab 2 about this, right? Indicators, maybe. Where it's specifically in a pH range, it changes color. So methyl orange below 3.1 is what color? Red. And above 4.4, it will be yellow. In between, some of it will have changed, right? So it's going to look orange in color for most of it, right? Because some of it will have changed, but by the time it gets to 4.4, all of it will be yellow. Okay, below 3.1, all of it is red. In between, I don't know how much has changed or not, okay? And all of the indicators follow that same rule. You just have to be careful because one's like from Cresol green doesn't have anything to do with green, right, as one of its options, okay? Do you know which one of these indicators is most common in a titration? It is. We look usually for the pink color. So phenolphthalein is the one used most often in pink. Another way they could ask the question is like, in a strong acid, what color would this be? Okay, so for example, for litmus, in a strong acid, what color would it be? Well, strong acids are what numbers? Close to what? Closer to 0 or closer to 14? 0. So it would be red, right? If we had bromethymol blue in a strong base, what color would it be? Blue, right? Strong base close to 14, right? So remembering just that from 0 to 14, here we have bases, here we have acids, closer to 14, strongest base, closer to 0, strongest acid. Here at 7, H plus equals OH negative. That is important to remember. They like to ask that question. So the concentration of H plus equals the concentration of OH negative at 7 only. When we get close to 0, we have more H pluses, and closer to 14, we have more OH negatives. Okay, so just kind of knowing that in terms of where things are in the pH scale. And then I guess we could just do this quickly about pH. If you change one number in the pH, the concentration changes, remember, times 10. So if you change from 5 to 6, there's a 10 times decrease in H plus. Why? Because the most H pluses are over here at 0, right? And I'm moving away from 0, so I have less H pluses. If I went from a pH of 9 to 7, right? Well, first, would my H pluses be increasing or decreasing? Increasing because I'm close to 0, right? And each hop, each number is times 10. So this is times 10 times 10. So how many times is that? It's basically, it was 10 times 10. 100. So it would be 100 times increase. Okay, in H plus. Okay, so that's as far as they get with pH. Decay mode, table N. So you could be asked about half-life, decay mode, either one. Also to complete a natural reaction, like a natural decay reaction. So for example, iron 53. I started writing its atomic number. When it decays, it produces two things. And when it's asked on the exam, it's going to give you 2 blanks, okay, to fill in. Well, when I look at iron 53, it says that its decay mode is B plus. So what is that? How do you find out what that is? Look at the very next table after N, so table O, right? And it's a positron, right? And so it looks like 0 plus 1 E, or you could write the B symbol, right? And then I have to figure out what's missing. Well, I need the atomic number for iron. How do I find the atomic number for iron? I just go to periodic table, right? So iron's atomic number, you got to go to the periodic table, 26. They already gave me the 53 on the top. So this is like the divider. If I have 53 on the top on this side, I need 53 on this side, right? So what does the top number have to be?
53.
Yeah, because that's a 0, right? And what will the bottom number be?
27.
Well, I want it to total 26, right? Because I want both sides to be the same. So if only,
So 25.
yes, so 25. because now 25 plus 1 is 26, right? And then I look at the periodic table, and which one of these numbers am I going to look up to tell me the symbol?
25.
Good, which is
And
M. So you could be asked to write it, in which case they will give you 2 blanks to fill in, or they could just have 1 blank left that you have to finish, okay? The one that people usually get wrong is something like this. All right, and why do they get it wrong? Well, nitrogen 16 has B negative, right? Which is a beta particle. So it looks very similar, but like this. What is nitrogen's atomic number? So I have the bottom number.
7.
Okay. So finding the missing top number is easy, right? It's just still 16, right? But when I'm looking at the bottom number, this is where people make a mistake, because as soon as there's a negative, everybody forgets how to do math, right? So I could set it up as an equation, like 7 arrow equals -1 plus whatever I'm trying to find, okay? So what number should go here? Yes. So that's the only one you really have to be careful on, right? And then what element is this? So you're going to always want to have a top number, bottom number symbol, top number, bottom number symbol, okay, when you do those. For half-life, remember that the amount goes down by half, right, each time. So just grab this part. So if I have 1 whole, right, after 1 half-life, half of it is left, right? In terms of a fraction, what fraction is left after another half-life? Well, just make, they should go to the front door, okay? 1/4, then after 1/4 is
20.
1/8, after 1/8 is, they don't usually ask past that, right? In terms of percent, it would be 100%, 50%, right? Will be next, 25%, 12.5, right? And continuing like that, right? Each one of these, so this is half-life number 1, half-life number 2, half-life number 3. So sometimes you're asked based on grams. So if I started with 200 grams, how many grams are left after 1 half-life? 100. After, like, how many grams? 50. After another half-life,
25.
right, then 12.5, right? So this is 1, 2, 3, 4 half-lives, right? If they want to ask how long did it take, then you need to know how long the half-life is. So for nitrogen 16, the half-life is 7.13 seconds, right? That means this half-life took 7.13 seconds. So did this one, so did this one, so did this one. So you can figure out total time, okay? So it's kind of just a few pieces. Sometimes they ask for fractions. Sometimes they ask for percents. Sometimes they ask it this way to find out how many grams. And then sometimes they ask it in terms of time. So you have to look up the half-life, okay? But so it's kind of a lot that is happening on this table, and they could ask the question a whole bunch of different ways, right? Table O, basically the only thing you should know for sure, beta particle is the same as a what? What is another name for a beta particle? Electron. So beta particle is an electron, okay? You should know that the top number represents mass, and the bottom number represents charge, or atomic number if it's an element. And then you should know the difference between penetrating power and ionizing power. So penetrating power is the ability to pass through things, okay? So in order, it goes like this, alpha, beta, gamma. This has the most ionizing power. And this end, gamma, has the most penetrating power. All right, so most ionizing versus most penetrating power. So if gamma has the most penetrating, alpha has the least, like it goes in this order, okay? So definitely have to remember that. They usually ask penetrating power, but I have seen them ask ionizing power, but penetrating power is the more common one. And why does it work like that? Because gamma has no mass and no charge, so it can like just pass through a whole bunch of stuff, okay, easily. Alpha particle has a pretty big mass compared to all of these things, so it gets stuck. Like you literally hold up a piece of paper and alpha particle can't get past it, okay? Gamma particles can go through thin lead, concrete. They can go through a lot, okay? And table O is used with a lot of table N, so those two kind of get paired together. Table P, we're using this to name any carbon chain or carbon branch. So if I had to name this, how many carbons are in that chain? 4, so it's the prefix for 4. Bute, right? And then do I see any double bonds, triple bonds? No, so it's just going to be butane. Good. If I have this, now while it's true I have 5 carbons, right? Are they all connected in a row? Can I get all of them in one row? I can't, right? So I still have butane, right? You told me that was the chain, right? But now I have this thing stuck on it. So how many carbons are here? 1. So the prefix for 1 is meth. And then what I do is add YL to say it's a branch, okay? And then I need an address because I could have put it over here. I could have potentially put it somewhere else. So this is carbon number 2. Most of the time they're not asking you to name one like this, but they could ask you to recognize it, okay? So definitely know that you have the chain and then branches still using the same prefixes, okay? All right, then for table Q, you should know only alkanes are saturated, right? Okay, the other ones in not being saturated, what are they? Unsaturated, right? So you know how to use table P and Q together to name them. So this no, that's right. Okay, so how would I name this? So first, are all the carbons connected in a chain? Yes. How many carbons are there? Okay, pent, good. Do you see any double bonds or triple bonds? Okay, so what is its name going to end with? The ene, right, for the double bond. And I need an address, right, to say where I put the double bond, okay? Remembering that I can be facing this way, but I can also be facing this way, right? So you have to think about the fact that you can turn the compound and rotate it the other way so that you pick the lowest number. So what lowest number carbon has the bond attached to it? You know, so this would be carbon. If I numbered this way, 1, 2, 3, 4, and 5, right? Or numbering this way, 1, 2, 3, 4, 5, right? So all of those options, what's the lowest number that's touching the double bond? 1. So I have to name it 1. I can't name it anything else. If you name it anything else, you're wrong. Okay? It has to be the lowest number. you can be asked to, like, if you have, you know, you could ask you, what's the chemical formula for, we'll just use pentene, any pentene, it doesn't really matter. So what's the chemical formula? So if you use this, it'll help you. So pent means how many carbons? 5, so it's C5H something, right? And the rule here says for alkenes, it's 2 times the number of carbons you have, right? So how many carbons did I have? 5, right? So it's double that. So it's C5H10. Okay. If I count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I still have 10, right? But I could do it without drawing it if I just know these formulas, okay? It'll usually be like, which of the following is saturated? And it'll give you a bunch of formulas, okay? So if I have this formula, is this saturated or unsaturated? So what you do is, how many carbons do you have? 3. Double 3, what do you get? 6. Do you have 6 hydrogens? So that means I have an alkene, right? So is that saturated or unsaturated? This is the only one that's saturated, right? So this one is unsaturated. What about that if I had C3H8? So same carbons, right? Still do double. What's double? 3 again, still 6. Do I have 6 hydrogens this time? No, I have more than 6, which means I added 2, right? So now I know it's an alkane, okay? Or C3H4, right? Double 3 is still 6. Do I have 6 hydrogens? No, I have less than 6, which means I use this formula, so it would be an alkyne, okay? So just from the formula, you can tell where it is, alkene, alkane, or alkyne, all right? All right, then table R, which lists a whole lot of stuff. I know you were here for review and we did a whole bunch with this table, so how do you feel about this stuff? Not bad? You remember about isomers? No? Okay. All right. So since you were here for most of the other stuff, I'll talk about isomers. So easiest way to write an isomer. So I'll do this. So here I have this compound, which would be, if I look at the name, I have to use an address and the prefix. So this is going to be, this way would be 3, this way would be 2. So this is 2-chloro-butane. The easiest way to make an isomer is to get a new address. What does that mean? Move the functional group. Can I move this to a different number? Like, could I have a different one? Because this address, this is 2-chloro-butane. So if I just did this, right? Now what is the number? What number do I use for this one? Remember, I have to remember that I can do this, right? Then I can reverse it, right? So 1-chlorobutane. So easiest way to make an isomer, first way is move the address, right? Get a new address. Second easiest way is if you don't have something that has an address like this. That's just 5 carbons in a chain, right? Like, I can't move anything in terms of, like, I don't have a chlorine stuck on there. I don't have an OH, I don't have anything. So what you do is you remove one of the carbons from the end and stick it on a middle carbon. So instead of having 5 in my chain, I will have 4, right? And then I put that carbon anywhere on a middle carbon. And then add your bonds for hydrogen. And these are isomers because they have the same molecular formula, but a different structural formula. Okay, same molecular formula, different structural formula. So if I count this up, this is still 1, 2, 3, 4, 5 C's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, same molecular formula, different structural formula. But there's a lot of information in table R, just make sure you look at it. Like you have example names, right? Functional group, like if it asks, what is the functional group? The only thing that you should write is something that's in this column, okay? If it asks, what is the class of compound? The only thing that you could write is what is in that column, okay? That's it. It's super straightforward. Periodic table. So pay attention to this, right? This is molar mass. That's gram formula mass for any element, okay? Electron configuration. This is ground state. So if it's listed on the periodic table, it's ground state. Do you remember how to write an excited state?
There's like one more.
Yeah, so you're going to take one and move it up, right? So I want to keep the total number the same. So for carbon, I could do this, 2, 3, 1. So I took one of the electrons and I moved it higher, right? I just can't add an extra electron. I need to move one that I already have, okay? So this is, you know, kind of the basics for the periodic table. So groups go in what direction? Up and down, right? What do they called when they go across? Periods, right? What's the name of group 1? Alkali metals, good. What's the name of group 2? Alkaline earth metals. What's the name of this section right here? Transition metals. What's the name of group 17?
No, it's the halixides.
Halogens, yep, halogen 17, and then 18 is noble gases. Which side of the periodic table is metals? Okay, what side is non-metals? And where are metalloids? Good, so which element that touches the zigzag line is not a metalloid? Good, aluminum. Aluminum is a metal. But boron, silicon, all the rest, right, that touch the line, those are where you get all your metals, right? Okay. Which elements on the periodic table do not react? Which group? Because they already have how many valence electrons? 8. And 8 is an octet. That's what every element wants to have, right? So look, its dream electron configuration is to have 8. What are the only 2 elements on the periodic table that are liquids? Like basically at room temperature. Mercury is 1. That's the only metal. The other one is a non-metal. It's a halogen. All right, it's this one. It's bromine. All right, so these are the only 2 liquids. So if they ask which of the following is a liquid conductor? Conductor means it's a metal, right? That means they're looking for mercury. If it says which of the following is a liquid insulator, right? Then we're looking for bromine, okay? Which elements on the periodic table are gases? You know which ones are gases? Well, obviously this group, right? Because what's the name of that group? Noble gases, right? But then there's 5 more. That's for the diatomic. So and most of them are diatomic, to be fair. So it's the rest, like the top part of group 17 plus N and O, and then this one, which is always the oddball, right? Because hydrogen is a non-metal, but it's like stuck over here. So group 17 is interesting because it has gas, liquid, solids. The only group on the periodic table that has all the states of matter, okay? And then when we're talking diatomic, that has an acronym. So do anybody remember the acronym? Yep, Brinkelhoff, right? So this. Brinkelhoff, that is the acronym for diatomic, which means basically, look, it's halogens again. Like they like to be involved in everything. They're like a little bit, you know, busy. So right here, here. Like that's a lot that are just in that same area. And then this one again. So when we're picking out the gases and we're picking out diatomic, a lot of them overlap, right? And they are the same. But all of the halogens are in this Brinkelhoff, okay? Does anybody remember how we could tell if an element is unstable based just looking at the information they give you on the periodic table? It has something to do with its atomic mass. It is. It's in parentheses. So if you look at 84, 85, 86, that's where it starts. You see how they're in parentheses? So if it's in parentheses, that means all of the versions, all of the isotopes are unstable. Okay, every single one. And this element right here is about the only element that's not up here that you'd ever be asked about. And this one, the name of it is not in table S. So you just have to know, what's the name of this element? Uranium, okay? But you can't find it in table S. Like they stopped listing at a certain number and uranium is not on there. So if you don't know the name of you can't find it anywhere on table S, okay? So that one you just have to know. The rest of them, you can find them on table S, so you don't have to stress about it. Let's see, so we covered that. Okay, how do you find valence electrons from the PS? Good, it's the last number, right? And this indicates how many energy levels it has. So it has 2 electrons in energy level number 1, right? And this has 4 electrons in energy level number 2. You should definitely know that. So when I look down a group, they have the same number of valence electrons, which is why they share similar chemical properties. So if it says which element has chemical properties similar to calcium, look for something in the same group, okay? An element that has similar chemical properties to phosphorus, you look for something in the same group, okay? In the same group has the same properties. When we go across periods, they have the same number of energy levels. We just keep adding more electrons. This has 1 electron in energy level 3. This has 2, then 3, then 4, then 5, then 6, then 7, then 8. We just keep adding to the energy levels that are already there, which is why the atomic radius gets bigger as we go down a group because we're adding energy levels, right? So instead of having just 1, now we have 2, then 3, then 4, then 5, okay, and so on. And then table S, you have to know periodic trends for this one and this one and this one. You have to know those periodic trends: first ionization energy, atomic radius, and electronegativity. Okay. Also, you have to know metallic properties. So which side of the periodic table did you tell me were metals? So as I go across a period, what happens to the metallic character? Am I going toward the side with metals or away from the side with metals when I go this way? I'm getting away from them, right? Which means the metallic properties would decrease, right? And then as I go down a group, metallic properties will, well, they will increase. So if I go back to the periodic table for a second, this element right here, francium, is the most, like the best metal. So if I move toward francium, it's more like a metal, okay? The best non-metal is right here, fluorine. So if you move toward fluorine, you're a better non-metal, okay? So when I go across a period, I'm more like a non-metal, right? And when I go down a group, I'm more like a metal, okay? So across a period, metallic properties increase. Across a period, metallic properties decrease. Down a group, metallic properties would increase, okay? If you remember, these are the two perfect ones, then you'll be able to hopefully make sense of it. States of matter, you should be able to tell. You have melting point. So melting point is changing from what to what? And boiling point means changing from, so that means if I have a temperature that is below the melting point, what state of matter do I have? Solid, right? If it is between the melting point and boiling point, I have a liquid, and above the boiling point, I have a gas. So if they say like, what state of matter is cadmium in at 500 Kelvin, then 500 is below 594, right? So it would be a, what state of matter would it be in? A solid. What state of matter would cadmium be in at 595 Kelvin? Liquid, right? So you just have to be able to read this. Like, it gives you so much information, right? You just have to know that it's there, okay? You know that you subtract electronegativity to find bond type. So anybody remember, because you have this one doesn't show up on there. We have non-polar, polar, and ionic. When we subtract electronegativity values, if we get something 0 or very close to 0, it's non-polar. When is it polar? When we get to what is the difference? Never remember. Is it?
It's 1.1.
I mean, it is. We start to for sure about 0.4 or 0.5, but 1.1 is a very good polar example. And then when we get to ionic, we're kind of above 1.7. Okay, so definitely remembering that, but it is not like cut and dry like that. If the difference is 0.7 and 0.9, this one is more polar. Okay, so you should be able to determine which one is more polar or which one is less polar by subtracting electronegativity. The only time you have to do that is when they're asking you if it's polar or non-polar. Usually if they're like, which of the following is ionic, you look for metal and non-metal. Okay, which is covalent, you look for all non-metals. Okay, you only have to subtract if they're asking you for non-polar versus polar. Okay, and then the last table, the formulas, you should know how to use all of these formulas. Okay. Remember, for the combined gas law formula, what does the temperature need to be in? Kelvin, right? So temperature has to be in Kelvin. Pressure and volume just need to be the same. I can tell you here is a spot where people make a mistake when it says solution. They're not asking you about the water itself, they're asking about the whole solution. And the solution includes the solute and the solvent. So if they have separated them in the question, you have to add them back together before you do the math, okay? This one, what reference table gives us this? Do you remember heat of vaporization, heat of fusion, and specific heat capacity for water? What reference table gives me that?
I want to say A.
Close, it's the one right underneath it.
Oh, it's B.
Yep, so table B is gonna give me all that info. Okay, don't forget about doing temperature conversions. Okay. remember most of these formulas, like once you have numbers, you could put like it over 1 to cross multiply if you need to. Like if I'm solving for mass in this formula, I could end up being, just do this. And then I could solve for mass.
What's gram formula mass again?
So gram formula mass is going to be the total. So let me give you an example for water, H2O. So I want to add the atomic mass for hydrogen twice to the atomic mass for oxygen. So hydrogen's atomic mass is 1, oxygen is 16, but I have 2 of these, right? So that's 2 plus 16, it would be 18 grams per mole, okay? If it was just H2, it would be 2 grams per mole. If it was O2, it would be 32 grams per mole, okay? And if it's anything else, you just have to add up the totals, and you want to use the atomic mass, okay? So that's what we're using from the periodic table, okay? Anything else? No?
Not for now.
Not for now?
Yeah, I gotta do it.
I know, it's a lot, right? So it's a lot, yes? Okay. Any other questions? I mean, the biggest thing, you really definitely have to use the reference table, right? So if you're stuck on a question, just like, I mean, skip it, come back to it, right? But like, look through the reference table. A lot of times, if you just look at the title of the reference table, sometimes you'll see keywords in the question, and you're like, oh, that's where I needed to go to answer that one, okay? So remember,